Hello everyone, I'm Emile Cadorel and today I will present you a paper entitled Online Multi-User Workflow Scheduling Algorithm for Fairness and Energy Optimization. My presentation will be divided into 4 parts. I will start by presenting an introduction of the problem that interests us today. After that introduction, I will present a modelization of that problem, followed by the presentation of the center of the contribution, that is to say the scheduling algorithm near deadline. I will then present experimental results obtained by executing the algorithm on a real infrastructure, and I will then conclude my presentation. Nowadays, scientists have gotten used to develop applications as scientific workflows. The scientific workflow can be defined as a set of tasks linked together by file dependencies. The interests of developing applications as a scientific workflow are multiple. First of all, it minimizes the complexity of the application. The tasks are simple and communicate through files. Workflows are then easier to understand, share, and customize. On the other hand, as the parallel parts of the application are perfectly highlighted, they are easier to execute and in a distributed environment. In the context of this contribution, scientists have access to a shared physical infrastructure. This infrastructure is composed of multiple physical machines that we will name nodes in the rest of this presentation. On the nodes, virtual machines, or VM, can be provisioned. One constraint can be noted: the different users want to have a guarantee of their data isolation, despite the sharing of the infrastructure. From that context, we can formulate a problem. Execute a set of workflows belonging to multiple users on the shared infrastructure. For each workflow, there is some uncertainty. 1. We don't know when workflows will be submitted by the users, and 2. We are not certain about the execution time of the tasks or the time taken by VM provisioning. VM being used to execute the tasks of the workflow in an isolated environment. In addition, workflows are highly heterogeneous in both software and hardware aspects. Software heterogeneity translated into the need of a task of a given operating system, a given library, etc. And hardware heterogeneity being translated into the need for a task of a certain amount of resources to be properly executed. That problem given, we have 2 objectives: minimize the energy consumption and maximize the fairness between the users. I will now give a more formal modelization of the problem we are interested in. The physical infrastructure is composed of a set of nodes. For each node, we have the following information. First, hardware information such as number of CPUs, quantity of memory, disk space, etc. And second, the frequency of the CPU. On the node, VM can be provisioned. VM have an operating system such as Ubuntu 20, CentOS 8, Windows 10, etc. VMs also have hardware capabilities such as 2 vCPUs, 8 GB of RAM, etc. and software capabilities referring to the software installed in the VM, Python, MATLAB, etc. The size of the VM can be arbitrary and does not need to follow a particular template. There is no over-provisioning considered in this contribution for efficiency reasons. Scientific workflows tasks assume to be highly CPU-intensive. For that reason, each vCPUs are associated with a real CPU core. We assume that the nodes are in the same local area network and that the bandwidth is homogeneous. Workflows are composed of a set of tasks and a set of files. To each task, we associate the following information: hardware requirements, representing the quantity of resources required by a task to be properly executed, 1 CPU, 1 GB of RAM, etc., an operating system, for example Debian 10, and software requirements, for example Python, MATLAB. Each task has input and output files. These files are computed by tasks and transmitted to other tasks to complete the overall execution of the workflow. Each file has a size in bytes that we assume to know. As said earlier, there is uncertainty during the execution of the workflows. In this contribution, we modelize the uncertainty by a Gaussian distribution. This is a common approach of the state of the art. By defining the uncertainty that way, we need 2 pieces of information: the average execution time and the standard deviation. In our context, the execution time is dependent of the node on which the task is executed. The same uncertainty modelization is applied to VM provisioning. We assume that the average time and standard deviation are given. However, this information can be acquired by sampling. The Gaussian distribution gives us a probability of ending time of the different tasks, or for a given certainty, an estimation of the duration of the task. Another important part of this contribution is the energy consumption. On the left of this slide is presented the energy consumption of a node. This consumption was acquired by running a variable number of CPU-intensive processes. One can note that the energy consumption is not linear to the load of the CPU. From that observation, we can infer a rule for energy reduction. By regrouping the tasks on the same nodes, the energy consumption can be reduced. For example, it is better to use a node at full capacity and let the other one in idle, than spreading the workload between the two nodes. I will now present the two objectives of the problem. The first objective is to maximize the fairness between the users. To modelize the fairness, we introduce the notion of workflow deadline and deadline violation. The deadline violation represents the amount of time spent by workflow execution past its deadline. The objective is then to minimize the sum of the deadline violation. An execution of the workflows of multiple users is considered to be totally fair if this sum is equal to 0. The other objective is the reduction of the energy consumption. This objective will be achieved by applying the policy described in the previous slide, that is to say, regrouping the tasks in the same nodes in order to use the nodes at the maximum of their capacity. I will now present the scheduling algorithm near deadline. Near deadline is a dynamic scheduling algorithm that is able of reconsidering the previously computed planning when new submission arrive. The algorithm considers the uncertainty of both tasks' execution time and VM provisioning time, as well as the uncertainty of new workflow submission by reconsidering the planning. The algorithm is able to take into account the heterogeneity of the tasks in both hardware and software aspects. This heterogeneity is solved thanks to the VM's provisioning. The workflow of multiple users are scheduled with the objective of maximizing the fairness between the users, and the algorithm takes into account the energy consumption. When new workflows are submitted for execution, the algorithm will assign a difficulty to them. The difficulty is defined by the critical path of the workflow and its deadline. The critical path of a workflow is the path in the workflow whose average execution time in the infrastructure is the longest. Once the critical path of the workflow is computed, we can compute the difficulty of the workflow as a subtraction between the deadline of the workflow and the length of the critical path. In this slide, there are two different workflows. The length of the workflow on the left is 80 seconds, and its deadline is 100 seconds. The workflow on the right has a length of 40 seconds and a deadline of 50 seconds. Then the workflow on the right is more difficult than the workflow on the left. The algorithm then schedules a given set of workflows submitted during a time window by increasing difficulty. Indeed, the lower the number of seconds left to execute the workflow, the higher the priority of the workflow. The main idea of the algorithm near deadline is, as its name suggests, to schedule the workflow near their deadlines. The idea is to keep space for future submission, whose difficulties can be higher than the difficulty of the previously scheduled workflow, without the need of reconsidering the whole planning. Another possibility would have been to schedule the workflow on few amount of resources. However, we have seen that the energy consumption of the nodes is not linear to their load. Thus, by executing the workflows on few resources, the energy efficiency of the nodes will be low, and more energy than necessary will be consumed. To explain the behavior of the near-deadline algorithm, I will present an example. In this example, we consider an infrastructure composed of two machines with one CPU each. In the figure presented, we can see that a planning is already computed by the algorithm, where a workflow composed of three tasks, X, Y, Z, is scheduled on a VM. This VM will be hosted by the machine 1 after instant 40. The VM takes a few seconds to boot, and the blue arrows represent the communication time. Now let's consider a new submission of a workflow with a deadline at time 50. To schedule this workflow near its deadline, the algorithm schedules the tasks one by one in reverse order. That is to say, starting with ending tasks. Tasks are sorted according to priority function. This function is detailed in the paper. The algorithm then starts the scheduling by the task D and tries to put it near its deadline. To be executed, the tasks need a VM to solve heterogeneity issues. Here there are two possibilities. To choose between these two possibilities, an heuristic is used. Or we choose the VM with the most tasks, or if both VM have the same number of tasks, we choose the location that is the closest to the deadline. Here we choose the location in machine 2. Then the task C is scheduled. There are again two possibilities, but this time a VM has more tasks than the other. This VM is then chosen and task C is placed on the machine 2. By choosing VM containing many tasks, we hope to consolidate the hosting nodes when they have more than one CPU, enhance their energy efficiency, and then reduce the energy consumption. We can see in red the deadline of the task C. This deadline is computed by the starting time of its successor. Then the task B. Here there is only one possibility. Indeed, by placing the task on the VM inside machine 2, the boot instant of the VM will be before instant 0. This is impossible. We thus place the task on the machine 1. And finally, the task A. We can see that none of the machine is able to execute the task in the allotted time. For that reason, the near-deadline algorithm considers that the scheduling failed. It removes the workflow from the planning and places it in panic mode. In that mode, every task in the planning with a lower priority than the workflow in panic mode is removed from the planning. In this example, we will consider that the workflow XYZ has a lower priority than the workflow ABCD. We therefore remove it from the planning. Then the workflow in panic mode is scheduled in best effort mode, meaning that this time the tasks are scheduled in standard order and as soon as possible. The algorithm schedules the task A. In our example, there are two possibilities. In that case, the location that gives us the earliest ending time is chosen. Here both locations are equivalent, so we choose arbitrarily the location on the machine 2. Then the task B. Here again, two possibilities, but this time they are not equivalent. If both of them finish at the same time, the location on machine 2 is to be preferred, as it is inside a VM with more tasks. Then the task C. Here the location on machine 1 finishes first, so it is the location that is chosen. In best effort mode, priority is given to execution speed over energy consumption. Finally, the task D. Here the two possibilities finish at the same time, so the location in the VM with the most tasks is chosen. The workflow is considered to be fully scheduled. The algorithm exits the panic mode. In the submission queue, the workflow XYZ that was removed needs to be rescheduled. This scheduling will be performed in standard mode. I won't detail this operation, but just say that the scheduling algorithm finds a valid location. One can note that the workflow is placed exactly where it was removed. However, I would like to remind that this example is just a toy example where parallelism is very limited. In reality, nodes have many CPUs, and removing workflow from the planning can have a strong impact for workflows with higher priority. I will now present some experimental results obtained by executing the scheduling algorithm in a real environment. To evaluate the algorithm, we executed the workflow montage. Montage is a typical case study used in the state-of-the-art to evaluate scheduling algorithms. This workflow regroups some interesting characteristics, such as data partitioning, aggregation, and pipeline. On the right of this slide, we can see the results computed by the montage workflow. This image was extracted from our experiments. We compared our algorithm with two state-of-the-art algorithms. HEFT, or Heterogeneous Earliest Finish Time, is a famous workflow scheduling algorithm. This algorithm regroups all the workflows of a submission in one big workflow and tries to minimize the max-span. The max-span is the overall execution time of the workload. We adapted this algorithm to take into account VM provisioning. The second algorithm we used to compare our algorithm is HEFT-deadline. This algorithm adds a deadline to the workflows, and instead of trying to minimize the max-span, tries to minimize the energy consumption. This minimization is made by regrouping the tasks on the same nodes. In our experimentation, we developed two different versions of our algorithm. We have seen earlier in the example that the VMs with the most tasks are prioritized. In the second version of the algorithm, instead of the most tasks, the VM with the most vCPUs are prioritized. We are aware that this experimentation seems unfair, as the HEFT algorithm does not try to minimize the energy consumption. However, to our knowledge, there is no other scheduling algorithm that can be easily adapted to our context. the majority of the state-of-the-art focusing their attention on public cloud execution in IaaS or fast infrastructures. An orchestrator was implemented in Scala AK. This orchestrator is able to take a planning computed by any scheduling algorithm and execute it. The only different part of the execution being the scheduling algorithm, we claim that this experimentation was performed in a fair environment. The infrastructure we used was Grid 5000. We used a cluster composed of 24 nodes, each one of them having 20 CPU cores. The workload was composed of 30 montage workflows, each one of them composed of 619 tasks. 20 of the 30 workflows were submitted at instant 0, and the other 10 were submitted at instant 50. The average execution time of a workflow montage is 250 seconds. The workflow submitted at instant 0 had a deadline of 1000 seconds, and the workflows submitted at instant 50 had a deadline of 300 seconds. Ubuntu VMs were provisioned to execute the tasks. The boot time of the VM were about 20 to 30 seconds. Let's remind that to guarantee isolation, a VM cannot execute the tasks of two different users. In this slide is presented the result of the experimentations. The table lists the different power usage of the execution using the different algorithms. The power usage was computed by comparing actual power consumption acquired by physical measurement on the nodes using PDUs, and the estimated power consumption if the nodes were used at 100% for the duration of the workload. One can note from that result that for the same workload, the near-deadline algorithm is able to reduce the energy consumption by 15% in comparison to Heft. Both near-deadline vCPU and near-deadline task have about the same behavior. This power consumption reduction can be translated into cost reduction for the infrastructure manager, as well as a reduction of the ecological impact of the infrastructure. The second objective of the near-deadline algorithm is the fairness maximization. We can see in the figure on the left of this slide the deviation between the expected deadline and the actual end time of the workflows. In this figure is presented the first and last quartile, the minimum, the average, and the maximum deviation. The deviation between the deadline and the actual execution time is well lower for the near-deadline algorithm, both versions having about the same behavior. On the other hand, because Heft regroups the tasks of all the workflows in one big workflow, it generates global synchronizations. Indeed, the different steps of the workflows are waiting for the end of the task of the other users, and in addition, because the VM cannot be used to execute the task of two different users, many VMs are booted, leading to a very bad global execution. Heft deadline does not regroup all the tasks of all the workflows together. However, because it does not reconsider the previously computed planning when new submission of workflow arrive, even if they have a higher priority, they are placed at the end of the planning. Thus, difficult workflows are waiting for the end of less difficult ones. For that reasons, near-deadline is better than Heft and Heft deadline in fairness maximization. I will now conclude my presentation. We have seen in this presentation a new algorithm for workflow scheduling with two objectives, fairness and energy optimization. This algorithm was compared to state-of-the-art algorithms in a real infrastructure by executing real and complex workflows. Experimentations have shown real benefits in terms of both fairness and energy objectives. We plan as future work to run experiments in a more complex infrastructure composed of multiple clusters. This will require for the algorithm to take into account the heterogeneity of the bandwidth. The second possibility for future work is to create a cost model that rewards the users that have submitted workflows with flexible deadlines. Thank you for your attention.